When you spend most of your day sitting, your body enters an active state of vascular and lymphatic accumulation. To identify the physical presence of this accumulation, press your finger directly into the tissue over your ankle bone for 5 seconds. If the skin leaves a small pit or dent before bouncing back, you are observing pitting edema. This is a clinical sign that interstitial fluid is currently stagnating in your lower extremities. This schematic illustrates why that stasis occurs. While the cardiovascular system uses the heart to move fluid through a closed loop, the lymphatic network, the system responsible for clearing cellular waste, is entirely passive. It has no central pump. Without a pump, your lymph relies on the mechanical force of muscle movement to clear toxins and dead cells. When your calf muscles remain still for hours, that flow halts, allowing inflammatory proteins to pool around your joints and organs. Bipedal ambulation provides the specific mechanical signaling that the body's internal systems require to maintain a baseline of metabolic balance. By tracking the chronological cascade of a 30-minute walk, we can see how this physical movement triggers a shift from immediate fluid clearance to long-term cellular preservation. Much of what is categorized as biological aging is the cumulative result of missing the physical signals needed to refresh the body's internal environment. The process begins at minute 1. As you step, your soleus and gastrocnemius muscles engage. As these muscles shorten and bulge, they act as a hydraulic pump, compressing the fluid-filled vessels nestled within the tissue. This rhythmic pressure forces the accumulated interstitial fluid and inflammatory proteins upward, clearing them out of the lower extremities and back into systemic circulation. At the cellular level, your leg muscles register an immediate drop in energy. This signals the mitochondria to begin multiplying, a process called mitochondrial biogenesis that increases the power-generating capacity of the cell. By minute 3, heart rate increases, accelerating the volume of blood rushing through the coronary arteries. This acceleration affects the endothelium, the single-cell thick lining of every blood vessel. The rushing blood creates mechanical friction, dragging against these cells, known as endothelial shear stress. This triggers the cells to secrete nitric oxide directly into the bloodstream. Nitric oxide drives vasodilation, relaxing the artery walls and making them flexible. This prevents the adhesion of arterial plaque and reduces vascular stiffness. Maintaining cardiovascular flexibility requires the mechanical friction of elevated blood flow to produce these essential vasodilators. Between minutes 7 and 10, the body shifts the primary fuel it uses for energy. Fat cells activate the lipase enzyme, which begins snipping stored triglycerides into individual free fatty acids. These fatty acids move into the muscle's mitochondria to be burned for fuel, achieving a state of lipid oxidation. At the 30-minute mark, the metabolic focus shifts toward the management of systemic blood glucose levels. This schematic shows the GLUT4 transporter, a protein gate embedded in the muscle cell membrane regulating glucose entry. Normally, this gate is locked, requiring insulin to bind to the cell before opening to allow sugar in. Walking creates a metabolic exception. Muscle contraction forces the GLUT4 gate open directly, bypassing the insulin signal. With these gates open, the active muscle acts as a vacuum, pulling glucose from the bloodstream to power movement. Walking 30 minutes after a meal aligns this insulin-independent glucose clearance with the moment blood sugar levels are at their highest. Active skeletal muscle functions as a mechanical pancreas, clearing blood sugar without placing additional demand on the body's insulin response. At this stage, your muscles transition from mechanical levers into dynamic endocrine organs that route chemicals throughout the entire body. This map tracks proteins called myokines, specifically IL-6, which are secreted by contracting leg muscles and move through the bloodstream to find clusters of inflammation. Muscle-derived IL-6 acts as a suppressor of systemic inflammation, directly neutralizing destructive cytokines like TNF-alpha. This chemical signaling eventually reaches the hippocampus, the brain's center for memory and learning. Sustained movement triggers the hippocampus to be flooded with brain-derived neurotrophic factor, or BDNF. BDNF drives neurogenesis, the process where neural dendrites begin extending and branching out to create new, fortified synaptic connections. Alongside this growth, the rhythmic nature of the walk drives a measurable drop in circulating cortisol levels. This reduction in stress hormones recalibrates the amygdala, shifting the brain's default state from high-threat reactivity toward a state of baseline resilience. Walking provides the physiological environment necessary to manufacture the neurochemicals that maintain cognitive architecture. The impact of this daily habit eventually reaches the subcellular markers of biological aging. Within each cell, your DNA is capped by telomeres, protective tips at the ends of your chromosomes. Every time a cell divides, these telomeres shorten. When they become too short, the cell can no longer replicate, leading to cellular decay. Consistent movement triggers the activation of telomerase, an enzyme that binds to these tips. This enzyme synthesizes new genetic material, effectively rebuilding and extending the length of the telomere cap. Data from UCSF and Stanford shows that regular walkers exhibit measurably longer telomeres than sedentary individuals of the same age and BMI. Low-level ambulation moves beyond treating symptoms. It works at the molecular level to maintain the integrity of your genetic code. To trigger this biological cascade, the focus is on Zone 2 intensity, maintaining roughly 60 to 70% of your maximum heart rate. Pushing into high-exertion anaerobic training actually lowers fat oxidation and can reduce the specific release of BDNF found in steady walking. The clearance of inflammatory fluids, the regulation of blood sugar, and the preservation of your DNA all rely on steady, low-intensity mechanical force. Human physiology requires the constant mechanical signaling of bipedal ambulation to maintain the structural, chemical, and genomic integrity of the body.